So let's talk about another pattern called reduce. Now, a reduction is basically an operation that's applied pairwise to each of the elements. And the typical operation is the parallel sum. Now, suppose you wanted to calculate the sum of all the elements in the array. If you were to do it sequentially, you would write out the sum as, the sum of the first two elements plus another element, and so on. And if I were to present it graphically, it would look kind of like this. And this isn't good for parallelization because each subsequent operation depends on the previous operation. So it seems like they're all tied together. But in this particular instance, we're in luck effectively because the addition operator is associative. So we can keep subdividing the problem space. So initially, if instead of calculating the sum from 1 to n, we can calculate the sum from 1 to n over 2 and add it to the sum of all the elements from n over 2 to n. And we can sort of keep going and subdividing it until we get something that looks very close to a binary tree. So something where all the operations happen pairwise and then they get paired up higher up the tree until the root, until the final addition operation. So in practice, the parallel reduction on the GPU would look something like this. Now, I know this looks a bit complicated. Let's go through this and actually discuss what's going on. So we're adding up n data elements, and here I'm using, well, for this example, I'm using one thread block of n over 2 threads. So here we have 8 elements, and we have 4 threads at the beginning that are going to perform the sum. And what effectively each thread does is it adds to the current data value, so the value it's mapped to, it adds the value that's next to it. So for example, here the thread at 0 would add the value to the right, so the value of 2 to the value of 1, and put it here in this cell as 3. And at each iteration, 2 things happen. So by iteration, I mean going from this step to this step. So at each iteration, the number of threads get halved. So here we're starting with 4 threads, then we have just 2 threads, and finally we have just 1 thread. And another thing that happens is that the step size is doubled. The step size is effectively the distance from here to here. So here it's 1, and then it gets doubled, so it's 2, and then it gets doubled again, so it's 4. And surprisingly enough, this operation, if you do it the sufficient number of times, it actually gets you the final result, and then the final result appears at the 0th location in the array. So let's take a look at how that would actually work on the GPU in code. All right, so let's make another project. Okay, I'm going to call this one reduce. Once again, I'm going to get rid of everything that CUDA generated for me, and we'll start from an empty file. So int main, same things as we've seen before, some count of elements, let's say 512, and calculate the size as well as count times. I'm going to use int for this one, so it's going to be size of int. All right, now I want to initialize the host array with the values going from 1 to 512, because then it would be obvious for us if we're actually calculating the right thing. So int h with the size of count, and then for I going from, going from 0 to count, we're going to say h at I equals I plus 1. Because we want values starting at 1, not starting at 0. Okay, so let's allocate the device memory for it. So CUDA malloc d size, and then copy h onto d. So CUDA memcpy d comma h comma size comma CUDA memcpy host to device. All right, and this is where we would call our kernel. I would call it just some single block. And as I mentioned previously, there's going to be one thread block, and the number of threads that we need, the maximum number of threads, is count over 2. So let's have that many threads, and we are only passing the array D, which means that after we're done, the D array, it would effectively be reused. So this means that if you need to preserve the values in D, well, here we're preserving them in host variable, but if you needed to preserve them for some reason, you would need an additional array to store the intermediate calculations. Let's write up the kernel now. This is going to be global void sum single block int D. All right, let's get the thread index first of all. TID equals thread index.x. And now we need to remind ourselves of what the rows are. It wasn't a particularly simple calculation that we were showing in the diagram. So I'm going to take it slow and hopefully you'll understand it. So we have a number of participating threads. I'll call it thread count. So thread count is number of participating threads. And this thread count, it begins at the largest thread count. So you remember we started with as many threads as we specified. So that's blockdim.x. Whoops, blockdim.x. And it has to be greater than 0, obviously. And it keeps going down, but it goes down by a factor of 2. So each time the number of threads gets halved effectively. And we can write it like this. Or I could have just divided by 2, but this is kind of neater. I shifted. Now the thread that is allowed to write has to have a thread ID less than the thread count. So thread must be allowed to write. So the other threads, they exist, they just don't do anything. So we say if the thread ID is less than the thread count, so the number of threads that's allowed to write, then we can do something. And now what we need to do is we need to calculate the locations where we actually need to write and where we need to get the extra data to be added up to the current cell. So we need positions of A and B to do A plus equals B. So int PA, the position of A in this case, it is our thread ID, TID, times the step size, and we haven't introduced step size yet. So you remember on the diagram we had the step size that doubled each time. So the number of threads halves each time, but the number of threads doubled each time. And I'm actually going to add it to this for loop just to be explicit about it. We could get it from the total thread count, but this is a bit neater this way. So step size begins at 1. And it keeps decreasing again by a factor of 2. So that means step size shift left by 1, like so. And there is no stopping condition for the step size because we have a stopping condition for thread count, and that's good enough. So the thread ID times the step size, but remember that we originally started with half as many threads as we have input elements, so we need to multiply this by 2, like so. And then the data that we're adding to A, PB, is going to be PA plus the step size. So we're adding whatever is to the right of the current element to the current element, and then we're doing D at PA plus equals D at PB. All right, so we're done writing this. We can now actually test this. Let's finish off the main method first. So cout, let's put sum is result, and then we need to free the D array. Pause the program, turn 0. All right, so we're doing a sum from 1 to 512. Let's actually run this. Aha, yes, we forgot to actually get the result from from our calculation. So let's do that. So we have int result, and then we do a CUDA memcpy to result. Notice I'm not declaring an array here. I'm declaring a single value, but I can take a pointer to it and just write a size of int to that location. CUDA memcpy device to host. There we go. All right, this should work. Alright, so according to our calculation, the sum is 131,328. Let's actually verify this. Alright, so sum from 1 to 512, 131328. Looks correct. But of course, we want to see how it actually happens on the GPU. So let's stop this debugging process and go into the kernel and actually see what's going on. I'm going to put a breakpoint here, and I'm going to reduce the number of elements to something manageable, let's say 32. So don't forget, we need to build before we start CUDA debugging, because this button here doesn't cause a rebuild. So let's do this. Alright, and now let's start debugging, and we'll use the CUDA warp watch to actually see what's going on inside the kernel. Alright, so here we are in the kernel. What do we want to look at? Well, we probably want to look at the values of D. So D at thread ID. But of course you have to realize that this will only give us half of the values, because the other half is, well, it's also participating in the calculation, but because thread ID is half the size of the overall number of input elements, well, how do we deal with it? Well, the answer is we simply do it like this. D at TID plus 16. I know it seems a bit like cheating, but we get the rest of the values. So that's our input array. You can see that at the moment nothing bad is happening to it. It's doing just fine, and it's got values from 1 to 32. Let's press F5 once. Ta-da! You would see that every other value has changed. So 2 has been added to 1 to give 3, 4 has been added to 3 to give 7, and so on. Let's press F5 again. And now every fourth value has changed. And now if we keep doing this, that's every 8th value, every 16th value, and finally we get 136 plus 392, like so. And that's it. So here's our result, 528. And that's the gist of parallel reduce.